Okay, this example is somebody looking at a car as it's driving around, and just even though there's only 2 eyeballs, for simplicity, I coded it up as though there were 4 eyeballs, and at time 0, you have 2 eyeballs that are looking at the car at time 0, and at time 2, you have 2 eyeballs that are looking at the car at time 2. And we're going to build on this in the next example, but for now, I want you to sort of keep this model in mind. And the inspiration for this was the saccadic masking video, which I highly recommend, about saccadic masking. And what they did is they simulated what happens in the human brain when you move your blind spot across the screen. You actually are moving your blind spot at just the right time, and you can't actually see a motorcycle on the road. And so they're encouraging you to change your scanning patterns with your eyes so that you're less likely to get tricked by the saccadic masking. Very interesting video. Okay, so let's go ahead and see what's going on here in the code. We have our usual imports like we've been doing, and we're going to look at vehicle 0 and 2, and later we will add vehicle 1, but for now vehicle 0 and 2. And we're having 2 eyes at 2 different times, so that's 4 different eyeballs, and each one gets an angular measurement, okay? And for the vehicles, they have 2 dimensions of data. So you pretend like everything's happening in the plane, okay? And I'm putting the eyeballs at 1 and -1 on the y-axis. And we actually don't necessarily need the weight anymore. This was left over from the Fox code, and so I left the weight in there, and that is actually not necessary because you can see actually maybe we do need the weight. Oh, we do need the weight. That's right, because we're dealing with angles and distances. Yes, so we do need the weight. Okay, and we can go ahead and run this code, and you can see that one vehicle, that's vehicle 0, is projecting out to the 2 eyes at time 0, and vehicle 2 is projecting out to the other 2 eyes at time 0. So that's kind of silly, but our graph reassures us that we actually coded that correctly. And the consistency radius started out pretty bad and went down. I actually have typed in the expected answer so that it spits it out to remind me each time. So as I change the code, I can come back and see, did I actually get it or not? Okay, so let's see. I was supposed to end up with vehicle 0 at -515. I'll say we made it. Vehicle 2 should be at 10.5. Great, and my consistency radius should be close to 0, and it is. So what I can do is I can change the initial guesses as to where the cars were. And I already started them at 0, 0. So this is already pretty far away from, where I expected it to be. Let's just see if I knock one of them off a lot, if I can still find it or not. See, this is what I don't like about this graphing software. It prints it differently each time. So it was pretty bad. This is pretty bad. This is weird because it gave a really decent consistency radius, and it completely did not find either of the vehicles. So sometimes you have to stay, pretty close to your solution, or the thing just runs off course and it doesn't know what it's doing. So this case is really bad again. So let's put it back at 0 and see what happens. We already did 0. Let me see what happens if I knock this one off. There we go. Okay, that's not too bad. So it can handle a little bit of wiggling around, not too much, and we will continue talking about this on the next video.